Test, test.
All right, well, welcome back from tea time, and we will recommence this week's seminar with Mathias Braun of the University of Toronto, who will be speaking on Timelike curvature dimension conditions for Lorentzian spaces via Rényi's entropy.
Okay, thank you very much for the kind introduction, including the correct pronunciation of my name. And also in general for giving me the opportunity to talk at the seminar, and even more generally to those responsible essentially for having me here and being part of this thematic program, and to sort of give you an overview over very recent work I just uploaded to the archive. So just as a announcement, this will be a quite mathematical talk, although I try to keep things at a very informal level, so that I hope to get everyone still into the boat. And there will also be certain things I have to repeat from what Robert just said, but I do not really regard this as a disadvantage. I mean, since there were, I think, lots of people that are interested in diving into this field of synthetic time-like lower Ricci curvature bounds for Lorentzian spaces. I think it's a good opportunity to repeat things as much as possible. So my talk basically will be complementary to what Robert just introduced to you. So I will show you a notion of the time-like Ricci curvature of a Lorentzian space to be bounded from below by k, and the dimension to be bounded from above by a parameter n, in a somewhat different approach than the entropic one that has been outlined to you by Robert. Okay, so before actually getting into definitions, let me come to the actual setting in which I work with, and sort of the approach I'm going to take is somewhat sort of the reverse one to compared to Robert's talk. I will directly start with, let's say, the non-smooth descriptions, rather than starting with the smooth manifolds and deriving the non-smooth theory out of it. So the setting in which I will work will be the one of a proper, possibly incomplete metric space. And what you should really think of this M to be is really this is your given, possibly highly non-smooth space time in which you are essentially doing general relativity. It will be endowed with a radon measure. And so up to now, this is essentially the definition of a metric measure space, and the Lorenzian structure really comes into play by these three additional objects here, axiomatically. Sorry? Bounded closed sets are compact. Yeah, probably I messed up a little bit. Yeah. Thanks. What was the point? So the additional Lorentzian structure you are incorporating here in these data, MDM, is a notion of chronology between between point pairs of M. And if such a chronology relation holds, you will say that X is in the timelike, not in the chronological past of a point Y, and vice versa, Y is in the chronological future of a point X. Yeah, by default, you also endow the space with the notion of causality between points in the in an evident non-smooth adaptation of the respective smooth Lorenzian terminology. And what you require this causality relation is that chronologically related points should always be causally related as well. Yeah, and sort of this chronology and causality relation have a very close interaction with the third object here, the so-called time separation function tau, which in the language of Robert's talk is just the positive part of the function L that he introduced. Which obeys a certain bunch of properties that all essentially arise from the interpretation of tau xy to be the maximal proper term that a space-time point x needs to travel to y. Yeah, so the first property that you might want this time separation function to obey is that if your points x and y are not even causally related, then you better not want any positive proper time to pass when you sort of make this impossible travel from x to y. Then secondly, tau should detect chronology of space-time points x and y. Namely, you require tau to be non-vanishing only on chronologically related pairs of points. And the last property that also appeared in Robert's talk is sort of the reverse triangle inequality along causally related triples of points. Yeah. And for just as an announcement for those who come from the CD space community, the later formulations of the curvature dimension conditions that I will give to you will be formulated in terms of this time separation function instead of the metric. Yeah? So the time separation function will take over the role of the metric that you, from the notion that some of you might be familiar with. Okay, given all these data, all these 6 data, I call the induced sextuple a measured Lorentzian space, and I abbreviate all these data so that I do not always have to repeat them just by curly X for convenience. And so just as an example for those who maybe still do not have a real imagination of what this such a measured Lorentzian space should be, it of course in quotes includes smooth Lorentzian spacetimes, but you can lower the regularity in a quite significant way. So the class of measured Lorentzian spaces in fact also includes globally hyperbolic and causally plane Lorentzian spacetimes. And causal planeness is just a condition that essentially prevents something like a bubbling phenomena and something like this. And it will always be satisfied for Lipschitz continuous metrics. Just at a very technical level, it is not even required. It is up to some extent not even required to assume causal plainness, but there are certain further background assumptions that I do not go into detail with for technical reasons, for which this causal plainness is really useful. And also what is included in this setting is a recent Lorentzian adaptation of the construction of metric cones, which goes under the name of generalized cones, which also fall into this category. So yeah, so this framework really covers a broad diversity of possibly very non-smooth Lorentzian spaces or weak solutions to the Einstein equations, if you want. Okay, as Robert already outlined to you, so the basic idea of how you formulate synthetic notions of the Ricci curvature bounded from below by some constant k in timelike directions and the dimension to be bounded from above by some other parameter is to formulate these things in terms of convexity properties of some functional, I'm going to define to you in the next slide, along a certain notion of chronological geodesics. This has already been defined more or less in the talk of Robert, but still I think it's useful to recall the respective notions. So everything is sort of phrased in terms of an optimal transport approach. The optimality here is measured by the total transport cost, LP, defined for exponents between 0 and 1 in the way depicted here. So given two mass distributions mu0 and mu1, the corresponding transport cost is defined as the supremum over this integral quantity here, involving the time separation function tau over all so-called causal couplings of mu0 and mu1. And rather than giving you technical definitions of this, let me maybe illustrate to you the notion of a coupling, of causal couplings, and what this has to do with chronological geodesics, rather by a picture, because I think that's more illuminating. So you have two space-time mass distributions, mu0 and mu1. You want to transport or couple with each other. So as maybe all of you know, a coupling of two probability measures is just a measure on a probability measure on the product space that projects down to mu0 and mu1 respectively. And a more heuristic way of how you should think of a coupling is sort of it assigns a way to match point pairs x and y, where x belongs to the support of mu0 and y belongs to the support of mu1. So this is the very heuristic interpretation of this. And as soon as you can achieve this in such a way that pi almost every point pair x and y is in causal relation to each other, you call the corresponding coupling causal. Yeah, and so the concept of a coupling is a very convenient tool to incorporate the Lorentzian structure of your possibly non-smooth base space. Yeah, and in an evident way, you also can define what for a coupling to be what it means for a coupling to be chronological. Yeah. So what the approach we are going to take is sort of asking us is not only to assign or to study in which way or essentially how to any 2 points can be matched with each other, but also follow the trajectories along which this optimal transport happens. And this goes has very much to do with the notion of a chronological, or more precisely an LP geodesic. So the idea is that you follow the trajectories along these optimal transports here. Yeah? And the induced definition is the one of an LP geodesic, or more precisely a Timelike proper time parametrized LP geodesic, which by definition is just a curve mu t in the space of probability measures over M, for which there exists a so-called LP optimal geodesic plan, which is a measure on path space over M, such that at every t, mu t is just a push forward of this bold pi by the evaluation map at time t. And you require this optimal geodesic plan to be concentrated on so-called Timelike proper time parametrized geodesics, gamma on M. And by Timelike proper time parametrized, I essentially mean this relation. So the first equality sort of defines what it means to be proper time parametrized. And the second strict inequality here sort of means or says you what it means for a geodesic or for a curve to be time-like. Yeah, and sort of the idea behind this is that you follow the trajectories, or your plan bold pi is sort of a set of curves with starting points in mu0 and endpoints in mu1. And if you take the t slice of this bold pi, you get some sort of you get a cloud of t intermediate points of such paths, and these should constitute your mass distribution mu t at time t. Okay, so this is the
Mathias,
very rough. Yeah.
Can I ask a question? Just it might be very naive. So there is a unique coupling between mu0 and mu1, or in general no? So you pick one, and for each one you can define LP, or is that, or you also doing the
So the
supremum.
transport force will of course coincide, but the coupling itself is not unique in general.
So definition of length is therefore for all the possible couplings, or
so maybe I do not understand your question.
So the coupling, the set of couplings is a big convex set, but when you perform this supremum, so you're maximizing the expectation of the proper time between each initial pair and its partner, and that the resulting maximizer may or may not be unique. So in the smooth case, if mu1 is well in the future of, if every point in mu1 is well in the future of mu0, then the maximizers are unique. But if it's not true that every point of mu1 is well in the future of mu0, the uniqueness of the maximizer becomes a more delicate question. You're maximizing linear functional on a convex set, so you can hit a vertex of the convex set, or you can hit a space of the convex set. Does that help, Ghazal?
Yes, yes, it does. Thank you.
Sorry, I also have a question. Why in this definition you seem to require that that mu is concentrated on geodesics? In the usual metric case, this is sort of follows, right? That Wasserstein geodesic, I mean, it's a consequence of being a Wasserstein geodesic that it sits on geodesics in the space. But here, that's somehow not automatic.
To answer this maybe mathematically and very technically, so there is really a technical reason for this, at least the way I imagine these geodesics, because this notion of geodesics will have sort of nice compactness properties if you require them to be if you just define them in this way. So because, for example, geodesics in the Lorentzian case with respect to proper time do not have to be Lipschitz continuous.
Right. No, but are there some natural conditions, maybe some stronger conditions on these measures where this is sort of automatic? That
you get a plan, you mean?
Right. If you can think of it right away.
I think
it's just a little strange to me that here you have to put it as part of a definition, but okay.
I think there are two issues that it sounds like are being mixed up, at least to me, which is that whenever you have a coupling between mu0 and mu1, you can always join, mu0 almost every pair xy by a geodesic, and so you can always get a plan on paths that corresponds to that. Now, the question of whether almost every mu0, almost every x corresponds to a single y or not is another question.
Right.
But even the answer to that is no.
No, but my other question was that it really moves along geodesics, right? That in a space. That let's say you have that this mu t is that for almost every point the corresponding curve in space is a geodesic in space, or Timelike geodesic in space.
Well, that's by construction as long as the geodesics exist. Yeah. I don't remember whether we assume that we're already in a geodesic space or not. But.
Yeah, the problem has a little bit to do with the question whether or not the space of probability measures over a Lorentzian length space is a Lorentzian length space, and in fact vice versa. Yeah, I think what you are talking about is that if the Wasserstein space is geodesic, then also the base space is geodesic, something like this result.
Well, the general relation between geodesics and
this is not yet clear. So.
Okay, all right. Thanks.
Okay, so welcome. Further questions? Okay. So before I move to the definition of the curvature dimension conditions, let me just move on with two other definitions. The first one already appeared in the talk of Robert in a slightly different formulation. Maybe I try to give you a certain different perspective on this. So by Cavaletti and Mondino, it has been defined that a pair mu nu of compactly supported mass distributions is time-like p-dualizable if there exists an LP optimal coupling between them, which is also chronological. Yeah? While such a pair is called strongly time-like p-dualizable if it's time-like p-dualizable and there exists an LP cyclically monotone set gamma, which sort of detects LP optimality of causal couplings between mu and nu in the way I wrote this down here. So this definition as such maybe might not be very edifying to you, especially for those who are not experts in the theory of optimal transport. Oops. So in particular, I will not define to you what an LP cyclically monotone set is, but the way you should think about time-like p-dualizable pairs or strongly time-like p-dualizable pairs is that essentially strong time-like p-dualizable asks for all couplings or for all LP optimal couplings between this pair to be chronological, while time-like p-dualizability asks only for the existence of one chronological LP optimal coupling. Yeah? So this is the sort of difference between these two notions. And they will become relevant in the definitions later. As an example, if the supports of mu and nu are well distinct in such a way that every point in the support X lies in the chronological past of every point Y in the support of nu, then the pair mu nu is more or less by default strongly time-like p-dualizable. And the second definition is the one of the entropy functional that you will, or that we will later require to be convex in a certain sense, namely the Rényi entropy, which with respect to the Lebesgue decomposition of a given probability measure mu, with respect to the reference measure m, with density rho plus possibly some singular part, is defined in the way written down here. And this is really the point where, say, the reference measure comes into play, because before we were not really dealing with the reference measure, but the entropy functional sort of is the guy which encodes the behavior of Lorentzian volume, let's say. Okay, so after all this preliminary stuff, let me finally move to the definition of the TCD and the reduced TCD condition. I will start with the TCD condition, so for which I fix an exponent p strictly between 0 and 1, a number k, which will eventually play the role of the time-like lower Ricci curvature bound, and a number n, which will eventually play the role of the upper dimension bound. Boom. So here's the definition. So we say that a measured Lorentzian space X satisfies the time-like curvature dimension condition TCD pkn, respectively the weak time-like curvature dimension condition weak TCD pkn, if for every pair mu naught and mu 1 compactly supported, absolutely continuous with respect to the reference measure, there exist both a time-like proper time parametrized LP geodesic joining them and a chronological LP optimal coupling pi between them, such that for every t and every n prime you have sort of this maybe strange looking inequality for the Rényi entropy applied at mu t, bounded from above by this little bit complicated looking term on the right hand side. The only distinction between the strong and the weak TCD condition is whether I require this inequality here to hold between every time-like p-dualizable or between every strongly time-like p-dualizable pair. And there will be a certain evidence why it's useful to, let's say, take both definitions into account. So this is not just a matter of me being indecisive of which definition I find better. This is really, this will really be evident in the sequel. So here the tau kn are distortion coefficients involving generalized sine functions, which are of course well known to all of you who come from the CD space community. On the other hand, I think for non-experts, I do not find their definition very edifying, so I skip it. and rather provide you with an example where these distortion coefficients really take a very simple form. Namely, if you consider the case of k equals 0, then the distortion coefficient tau here is just equal to r, and hence these distortion coefficients here will not depend on the time separation function and drop out of the integral. And what you will eventually end up with is this sort of convexity inequality for the n prime Rényi entropy. And this is why I will also always call this maybe a little bit more complicated looking inequality, or also displacement convexity or displacement semi-convexity inequality. Yeah? So just as to give you an idea of why this is really something you should call convexity or semi-convexity. There is also an analogous reduced timelike curvature dimension condition. So we call X to satisfy the reduced TCD condition, respectively the weak reduced TCD condition that I endow with an additional star here in this TCD, respectively weak TCD. In fact, so the only difference between the non-reduced curvature dimension condition is the choice of distortion coefficients. So there are essentially slight variations of these tau distortion coefficients, namely the sigma distortion coefficients. And this is really the only difference to this non-reduced curvature dimension condition. And also in the case k equals 0, they essentially reduce to the same inequality as in the non-reduced case, and in particular the reduced and the non-reduced version for k equals 0 will be sort of the same, but in general this will not be the case. And so just to summarize for all of you, I have now introduced 4 new curvature dimension conditions, plus the 2 that Robert introduced to us are now 6 different curvature dimension conditions for Lorentzian spaces. And one of the major goals of my talk is sort of to clean up a little bit this jungle of curvature dimension conditions and show to you the relations between them and also what are the respective advantages of either formulation. Yeah? So before I actually get into results, let me just mention that the TCD condition, respectively weak TCD condition, is the Lorenzian analog of the CD condition after the CD space work of Theo Sturm. And the reduced TCD or weak TCD condition, respectively, is the Lorenzian analog of the CD star work of Bacher and Sturm in 2010. And as I mentioned already at the beginning of the talk, this sort of complements the entropic approach to time-like lower Ricci curvature bounds for Lorentzian spaces done by Cavalletti-Mondino after the approach for metric measure spaces by Erba, Kubada, and Sturm. Okay, just as a first take-home message, I want to learn is that now essentially all finite dimensional CD conditions for metric measure spaces, at least those who are formulated in terms of optimal transport, now have counterparts for Lorentzian spaces. Yeah. Okay, so that's sort of the historic overview. Let's dive into first results, namely first, let's say, quite elementary relations between these new curvature dimension conditions. So as a matter of fact, the TCD condition always implies the reduced TCD condition with the same parameters, while the reduced TCD condition will always imply the TCD condition, but with a certain loss at the level of lower Ricci curvature bounds a priori. Yeah. And this is really an analogous chain of implications holds for the respective weak versions. And this is there's really not much theory behind this. This just results from an easy pointwise inequality between the respectively involved distortion coefficients. Yeah. So if you want to interpret this proposition in a little bit more sophisticated way, it tells you that the TCD condition and the reduced TCD condition will always qualitatively satisfy the same geometric functional inequalities, whatever you are able to derive from this, but not necessarily quantitatively, yeah, which is just encoded by the fact that you have to pay a little price at the level of lower Ricci curvature bounds if you pass from reduced to non-reduced. Yeah, and I recommend to you to keep in mind, especially this second arrow here, because this will be relevant in the in later results or discussions. Okay, so the first cornerstone result of these TCD conditions is a stability result with respect to the notion of convergence of measured Lorentzian spaces that has also been introduced by Robert in his talk. So we will say that a sequence of measured Lorentzian spaces xk converges to x infinity if, after embedding the sequence as well as the limit into a very large Lorentzian spaces while retaining the respective Lorentzian structures, which sort of says that you want causally related points to and chronologically related points to lift to this large Lorentzian space. And after embedding this, you require that the sequence of measures, or more precisely embedded measures, converges weakly, and weakly here means in duality with the space of compactly supported continuous functions on this large Lorentzian space. This is a pretty straightforward Lorentzian adaptation of a notion of convergence for metric measure spaces, with respect to which you have this stability result, or more precisely I should say weak stability result, namely if this sequence xk converges to x infinity in the sense of the definition above here, and xk obeys the TCD condition for every k, then the limit space will satisfy the weak TCD condition. And a similar implication holds for the respective reduced versions. And so first I want to give you a very, very rough idea of the proof. And when I say rough, I really mean very rough, because the actual proof of this theorem is 10 pages long. So and afterwards, I want to comment a little bit on why you cannot weaken the TCD assumption to weak TCD really a priori, and why you cannot improve the weak TCD deduction to strong TCD in a sense. Okay, so the very rough proof idea is that, well, you want to prove the weak TCD condition for the limit space. So you take two strongly time-like p-dualizable measures, mu infinity naught and mu infinity 1, absolutely continuous with respect to the limit measure. And sort of the very rough idea is to construct, by a back projection procedure, let's call this, a recovery sequence of measures mu k naught and mu k1, absolutely continuous with respect to the measure mk, in such a way that they are time-like p-dualizable. And once they are time-like p-dualizable, your assumed TCD condition comes into play and provides you with an LP geodesic and a chronological LP optimal coupling, witnessing this convexity inequality for the Rényi entropy with respect on the space xk. Yeah? And sort of the very rough idea then in this inequality is to pass this to the limit, both at the level of geodesics and at the level of optimal couplings by compactness arguments, essentially. So out of the proof, there are technical obstructions that sort of tell you why you cannot weaken this and why you cannot really improve this, at least a priori. So in general, this recovery sequence constructed by back projection can only be constructed to be time-like p-dualizable in general. So in fact, in general, there's not really an evidence of why this back projected pair of measures should, while all LP optimal couplings of this back projected pair of measures should be chronological. But it is not so hard to construct this pair of measures in such a way that they admit at least one chronological pair LP optimal coupling. So this explains the TCD assumption here on the sequence xk. On the other hand, it is also not really a priori not clear how you can improve this to TCD, or in other words, whether or not you can drop strong time-like p-dualizability here to time-like p-dualizability, which has, in a sense, which very roughly speaking has to do with the fact that chronology is an open condition, and open conditions are not closed under, let's say, weak limits or so. Or more precisely, in passing to the limit k to infinity, both at the level of geodesics and of LP optimal coupling, in order for this time-like curvature dimension condition to be satisfied, you sort of still want things to be time-like. So both things should be, so the limits should better be chronological. But unlike LP optimality, chronology, as I said, is not stable under weak limits unless you know a priori that every LP optimal coupling of the limit marginals is chronological, because then you can appeal to the stability of LP optimality. So the limit of, let's say, LP optimal couplings will again be an LP optimal coupling. And since it's an LP optimal coupling between two marginals that admit only chronological LP optimal couplings, this will sort of by default be chronological. Yeah. So this is the technical reason why you can only reach weak TCD here. Okay, so as I promised, I'm going to clean up this mess of different curvature dimension conditions a little bit in the sequel, for which I need some preliminary preparation. Namely, I want to introduce you the notion of time-like essential non-branching Lorentzian spaces, which is a Lorentzian adaptation of a notion that has been introduced by Rayala and Sturm for metric measure spaces. So we call such a space X time-like P essentially non-branching if every LP optimal geodesic plan, those planes which constitute LP geodesics, is concentrated on a non-branching set of time-like proper time parametrized curves. And rather than giving you a definition of what non-branching set of time-like proper time parameterized curves means, let me maybe rather try to illustrate this by means of pictures. So two phenomena you essentially want to avoid in a non-branching set of such curves is that both you shoot off or you involve a time-like geodesics, and after some non-trivial time, these geodesics split into two separate time-like geodesics. And sort of the reverse, the causally reversed phenomenon is also something you would like to be not satisfied. So you do not want to shoot off two distinct time-like geodesics, but which sort of merge after some non-trivial time and then evolve as a single time-like geodesic. Now, while on the picture on the right-hand side, this is a nice, let's say, example of a non-branching, of a nice non-branching set. This sort of weakens the notion of a time-like non-branching measured Lorentzian space, which essentially asks all curves or all geodesics to be non-branching in a sense. And the way of how you should really think of this is that time-like non-branching is a condition on all curves to be non-branching, and time-like essential non-branching is a condition on almost every curve to be non-branching. Yeah, and I would regard this as very useful, especially in this business of synthetic Ricci curvature bonds, because these are formulated in terms of optimal transport, where you by definition, essentially deal with mass distributions and almost everywhere valid properties, for which time-like essential non-branching seems a little bit better suited. And let me maybe also underline this by a corresponding result for RCD spaces. So for metric measure spaces, the so-called Riemannian curvature dimension condition is stable under, let's say, measured Gromov-Hausdorff limits. And by the work of Rayala and Sturm that I just introduced to you, you know that the RCD condition implies essential non-branching of this metric measure space. So this is also the combination of these two results for metric measure spaces sort of give you an implicit stability result for the essential non-branching condition. Yeah, and since, as I have already learned from some introductory talks in this conference, people in Lorenzian geometry are really interested in taking limits and studying stability properties. This is let's say, at least an indicator that this time-like essential non-branching could be also quite useful. It may be, just a moment, better behaved condition under stability than pure non-branching.
So do you really need this for all LP optimal geodesic plans, or would it be enough to have it for, say, all the chronological LP optimal geodesic plans?
I think by definition, my LP optimal geodesic plans are chronological. Okay. And so once you have this Timelike P essential non-branching condition, the following theorem holds true, namely the strong reduced Timelike curvature dimension condition is equivalent to its weak version. And both of these are in turn equivalent to the respective entropic strong and weak TCD conditions in the sense of Cavaletti-Mondino. And so apart from the trivial implications in this diagram from strong to weak, this is already a quite interesting result, because a priori none of the reduced or the entropic curvature dimension conditions seems to imply the other one. And even, yeah, maybe even worse, if you want to put this adjective in quotes, I haven't been able to prove any of these of the non-trivial implications in this diagram in a direct way, but they are only provided in terms of a fifth equivalent property or characterization, which sort of is much better behaved under this essential non-branching condition, which is a pathwise version of the reduced TCD condition, which is the following. So if you have Timelike essential non-branching, then any of the above conditions here is equivalent to the following pathwise characterization to the reduced TCD condition. For every Timelike p-dualizable pair, mu0 and mu1, you can find an LP geodesic mu-t, interpolating them, and represented by an LP optimal geodesic plan, bold pi, such that at every t, the t-slice of this plan, or equivalently the measure mu-t, is absolutely continuous with respect to the reference measure, and its density rho t with respect to m obeys this pathwise inequality here, which is very reminiscent of, let's say, the integrated version, which in turn is just the reduced TCD condition. Yeah? So from an integrated version, you are really able to pass to a pathwise version. And this is a version where, which is much, as I said, much better behaved under essential non-branching, because essentially if you want to pass from weak TCD to the TCD condition, so the sort of the backward implication, you sort of want to cover parts of your Lorenzian spaces with chronologically related rectangles, and this pathwise interpretation of the TCD condition is much better behaved under, let's say, patching together these separate parts, yeah, very roughly speaking. And of course, just taken on its own, it is also just an easier formulation of the curvature dimension condition. Yeah, it does not involve any integrals or so. It's just a plain pathwise characterization, which is also sort of expected to bear better, let's say, or to encode better the geometric or structural properties of your Lorentzian space than maybe integrated quantities are able to decode. Okay, so as a remark, just similar pathwise interpretation is available for the TCD condition, so the one you do or formulated in terms of the tau distortion coefficients. But recall, there's still no equivalence of, say, this to this. So as I said, you know that the TCD condition implies the reduced TCD condition with the same parameters, but the same is not clear, at least if you insist on the parameters to stay the same yet. Okay, and sort of one of the last things I want to present to you is essentially the reason why you are actually entitled to prove what or to call what I introduced to you curvature dimension condition, namely the fact that this convexity properties of the Rényi entropy is in fact equivalent to lower Ricci curvature bounds in time-like directions and dimension upper bounds for Lorenzian spacetimes. So the corresponding theorem is that you take a globally hyperbolic smooth spacetime, say endowed with a Lorentzian volume measure, and then any of the TCD conditions that I introduced to you is equivalent to the Ricci curvature of this smooth time with respect to the Lorentzian metric to be bounded from below by k in all time-like directions. Yeah, and just as a very rough survey about how to prove this equivalence, at least the red equivalence here. is that, well, from passing from the TCD to the Ricci non-negative, what you essentially do is you just appeal to the equivalence theorem of the reduced curvature dimension condition to the entropic curvature dimension condition. And in turn, the entropic curvature dimension condition is already known to imply these Ricci lower bounds in time-like directions after works of McCann and Mondino-Sur. The backward implication is a little bit more involved. It really relies on the fine analysis of LP optimal couplings and LP geodesics on smooth spacetimes done by Robert in his work. So you can prove that every such time-like proper time P parametrized LP geodesic between a time-like p-dualizable pair mu0 and mu1 can be at least can be represented as the push forward of the initial measure mu0 by a certain map TT going from M to M, and this TT has some nice regularity properties that allow you essentially to run the subsequent computations. So first of all, it allows you to define a sort of Jacobian of TT, or more precisely of mu t with respect to the given reference measure. And then using Riemannian or Lorenzian computations, you can verify the logarithmic Jacobian to satisfy this, essentially the first differential inequality here. So that's just essentially Jacobi field calculus. So minus the second derivative of this logarithmic Jacobian will be greater or equal than this term involving the dimension plus this term involving the Ricci curvature. And the second inequality is then where you just put in your assumptions on the upper dimension and lower Ricci curvature bound, taking into account that the time derivative of TT is time-like. Yeah. And from this being phi t a logarithmic Jacobian, by exponentiating it, it is very easy to derive this second order differential inequality for the Jacobian jt raised to the power 1 over n prime. And the comparison theorem then gives you this sort of concavity property of the Jacobian raised to the power 1 over n prime. So it's essentially basically very similar computations as those which you do in the Riemannian case. At this point, it is maybe not completely obvious of how you pass from the sigma distortion coefficients to the tau distortion coefficients that you would need this TCD and the weak TCD condition to satisfy. And in fact, this is really something non-trivial because the sigma distortion coefficients are a priori smaller than the tau distortion coefficients. So you really have to appeal to the Riemannian structure a little and make a more refined analysis to pass from actually, I'm annoyed by this thing here. So you really have to do a refined analysis to pass from this inequality here involving the sigma distortion coefficients to get the same concavity inequality for the tau distortion coefficients. But once you have this, essentially the TCD condition or the TCD star condition then follows by just integrating up this concavity inequality. And just let me remark that you cannot only deduce this for non-weighted spacetimes, you can also derive a similar result, as I think also Robert told you about, for the entropic case for so-called Bakry-Emery spacetimes, where you replace the Ricci curvature by a Bakry-Emery-Ricci tensor and the reference measure by a weighted volume measure. And Bakry-Emery spacetimes have recently, maybe 2016 is maybe not that recent, but okay, have led to quite interesting singularity and splitting theorems. So it's nice to have them included in this setting as well. So other key outcomes that I just of the treatise that I summarized to you in the last at least topical slide is that as in the case where you start from the entropic curvature dimension condition, also starting from either weak TCD or the reduced weak TCD condition, yield time-like geometric inequalities involving the time separation function a la Brun-Minkowski, Bonny-Myers, and Bishop-Gromov. Yeah, so for those of you who come from the CD, CD or Riemannian geometry side, essentially these are the formulations that you know with respect to the metric, but where you replace the metric by the time separation function. Yeah. I still don't write them down for time reasons. Rather, I want to provide you with a corollary of either of these time-like geometric inequalities, namely if X arises from a continuous globally hyperbolic and causally plane spacetime and satisfies the curvature dimension condition TCD PKN, then the geometric dimension that has been introduced by Robert in his talk is no larger than the parameter n. And this is something, finally, which really distinguishes or favors the non-reduced curvature dimension condition, so compared to the reduced or entropic curvature dimension condition, because solely starting from the, or solely taking the geometric inequalities implied by the reduced or the entropic curvature dimension condition will only give you that the geometric dimension of M in the sense of McCann and Seemann is bounded from above by n plus 1. Yeah, although as Robert also told you, you are so starting at least from the entropic TCD condition, you are able to remove the plus 1 under a non-branching condition. On the other hand, this corollary here does not assume any non-branching condition. Yeah, so this is sort of what favors this TCD condition compared to the others, and is maybe also highlighted by the fact that by the diagrams I have presented to you, this TCD condition is simply the strongest one of everything. So it should imply the best geometric inequalities, and it does, thanks to this corollary, provide sharp versions of these geometric inequalities. Okay, so the last results I'm just collecting in this remark concerns time-like essential non-branching spaces. So what you are always, or what you are able to obtain, which maybe partly answers a question from Ghazal some minutes ago, is that under curvature dimension conditions plus time-like essential non-branching, you are both able to derive uniqueness of chronological LP optimal couplings and chronological LP, and LP geodesics, which essentially by definition are chronological. Yeah. So in time-like directions, essentially under nice conditions on the marginals, the optimal transport is basically done in a unique way. And the second result, which also would favor maybe the reduced TCD condition compared to the TCD condition, is a local to global property, which essentially, which you can interpret as a statement like, okay, if you have, if your Ricci curvature is locally bounded from below, in the sense that this convexity condition that I have just told you about holds on within the elements of an open cover of your Lorentzian spacetime, you can sort of globalize this. And this is a very, this is a highly non-trivial result, and deeply relies on the structure of the sigma distortion coefficients that you use in the definition of the reduced curvature dimension condition. And this property is just false for the tau diffusion coefficient. So it is a priori absolutely unclear of whether or not you can obtain a local to global property for the TCD condition. Sorry? Yeah. Okay. Yeah. Right. Yeah. Thanks. Okay, so that's essentially topically all what I wanted to tell you about work that has been already accomplished. So I want to use the last slide to give you an outlook of possible applications of this theory developed here. I would be very happy to discuss with anyone.
Sorry.
Yeah.
Can I ask a question about the previous slide?
Yeah.
So this is actually what I was trying to ask Robert in the previous talk. So you mentioned that there are versions of Banner-Myers and Bishop-Gromov.
Yeah.
And they're presumably sharp. So like, do you have rigidity results for equality cases in these theorems?
Not yet.
Not yet.
Not yet. I don't. I mean, I don't know. I don't know whether they are completely, let's say, parallel to the rigidity result for CD spaces, because these geometric inequalities involve the time separation function. And
yeah. Well, that's what I was wondering too. Exactly what I do expect to get, because it's a weak assumption, right?
Yeah. I mean, also, it says maybe I don't know. Maybe it has partly to do also with this corollary and the hypothesis of this corollary, because what you essentially need to relate. I mean, you sort of need to relate this geometric dimension to the actual quantities defined in terms of the metric.
Right.
Yeah.
Yes.
This is what Robert called local uniform convergence of tau as the metric goes to 0 in his talk. I don't know, maybe you have a name for it even, but so I mean, but yeah, you seem to agree that this is really a big question, whether or not this time separation function is helpful to get these rigidity results. That's correct. Yeah, there is not really a guess yet. So.
Thanks.
Okay, so the promised outlook. Let me maybe before I get into the list of open questions, let me maybe just point out a recent survey article of Cavalletti and Mondino, where they collect further possible directions of investigation. I will not address any of these, just for to shorten things a little bit, but just that Cavalletti and Mondino have also sort of collected a list of possible extensions that do not appear in my list. So the first, let's say, with this notion of time-like essential non-branching is, so the first evident question is whether the localization techniques and singularity theorems that have been developed under the assumption of time-like non-branching in the paper of Cavalletti Mondino, in fact, also hold under time-like essential non-branching. I'm pretty optimistic that this should be true. A much more delicate result would be what I would probably call Lorentzian globalization theorem after the result for CD spaces after Cavalletti and Millman. So recall that essentially under time-like essential non-branching, the reduced and the entropic curvature dimension conditions are equivalent to each other, and that this TCD condition implies the reduced TCD condition. And so the missing implication in sort of closing the equivalence of all curvature dimension conditions that are defined by now would be sort of the step from the reduced to the non-reduced curvature dimension conditions. And this is what in the CD language goes under the name globalization theorem. And it is a very interesting question whether a Lorentzian analog of this holds true as well. Then this has been probably partly addressed in the discussion after Robert's talk. So the very nice question would be whether or not it is possible to obtain a splitting theorem for, let's say, TCD 0n spaces after the result for RCD spaces with non-negative Ricci curvature bounds. Keeping in mind that in the Lorenzian case, there are by now well-established splitting theorems in the smooth Lorentzian case, say, yeah. And you could maybe try to draw this analogy to RCD or CD spaces even further, and given such a splitting theorem, maybe, and given maybe an appropriate precompactness theorem, could then lead to a structure theory for such TCD spaces after essentially after the work for RCD spaces by Mondino Neighbor and Brues-Semola. Sort of the result that you might maybe hope for is that almost every point, so the tangent space at almost every point of a Lorentzian space satisfying TCD is Minkowski space, something like this. This could be the direction of what Lorentzian structure theory is. And then intrinsically, it would also be, what would be an hypothesis? So the hypothesis in the Riemannian case is the R part, right? But from the R part, you have to prove that the only tangent space is Euclidean space. This is something. Of course, yeah, that's true, yeah. But as I said, so the step from, let's say, infinitesimal Hilbertianity as it has been defined classically to every tangent space being Euclidean is also already quite non-trivial. So yeah, but I mean, it's not clear whether this. No, for sure not. I think they are due to war. I don't remember. Sorry. I don't remember. Okay. Then intrinsically, it might be interesting to enrich the theory of TCD spaces by further examples. For example, one could just proceed and try to prove the TCD conditions, for example, for C1 spacetimes with distributional Ricci curvature bounds. This is just an interesting class of examples because for these are the lowest regularity spacetimes for which you still have singularity theorems, at least if you start from distributional Ricci curvature bounds. And it has been recently proven by Kunzinger, Oberguggenberger, and Vickers that an analog of the step from distributional Ricci curvature bounds for C1 Riemannian manifolds to certain CD conditions hold true. So there is sort of hope that the Lorenzian version of this holds true as well. And C1 spacetimes are sort of a regularity where you can still do things or expect to do things in terms of approximation of the metric. Then naturally it is natural to ask whether time-like sectional curvature bounds in the sense of Kunzinger-Sämann imply time-like Ricci curvature bounds. The corresponding results for CD spaces is due to Petrunin. And also it would be interesting to include the case of weighted Finsler spacetimes with lower bounds on their flag Ricci curvature. Given that there are recent very interesting splitting and singularity theorems for these spacetimes by Lu, Minguzzi, and Ota, and the corresponding result for CD spaces is due to Shinichi Ota. And as a very last comment, which is very vague, which I would also be happy to discuss with, let's say, the experts. In the world of CD, or more precisely RCD spaces, you know that the notion of feed flow is a very useful tool because it yields regularization properties. It yields even equivalent characterizations of Ricci curvature bounds. So in the Lorenzian case, is it meaning and or useful to use any notion of feed flow? Because, as I said, so from the Riemannian case, this is a very useful tool, technically. But on the other hand, I'm not so sure whether this is really something relativistic or not, or whether anything in this direction might be helpful or not. So this is sort of what I would also like to know or find out. And with this said, I am finished, and I thank you very much for your patience and attention.
So do we have any questions from the audience?